We have a point on the plane, so we can see here we have P naught, and we have a vector that is normal or orthogonal to the plane. Here's our normal vector right here. That would be enough to define the plane. And as we can see that, this n could be anywhere. If it's a normal to the plane, it is normal to every single vector in the plane. So remember, normal, orthogonal mean the same thing. I'm using the word normal vector. It means it's orthogonal, perpendicular, meets at a 90 to every single vector that's in that plane. So it doesn't matter where we draw n, it's going to be normal to every vector in that plane. So it's a way to define the plane. If we know a point on the plane and then we have this normal vector, we're going to be able to define it, as we will see. Let's look at this picture just a little bit closer. So we have our point P naught on the plane, and we have our normal vector n. Now we could draw or pick another point P in the plane, just some arbitrary point, and we could draw the vector that joins where we've got the tail of the normal vector and this point P. Now we could have vectors r that come from the origin then, and its tip is at x, y, z, and vector r naught whose tip is at our x naught, y naught, z naught, similar to what we had when we were looking at lines. So we can see that this vector whose tail is at P naught and whose tip is at P can be defined using the vectors r and r naught by taking r minus r naught. Now this vector needs to be normal or orthogonal to this vector here, and so how do we know that two vectors are orthogonal? We know if we dot them. So if I took n dot r minus r naught, that would need to equal 0. Properties of the dot product, we can think of distributing this through, so this equals n dot r minus n dot r naught, and that would need to equal 0. And so this is a way to express the plane in terms of its normal and in terms of a vector r that goes out to some arbitrary p and to the vector r naught that goes to the point x naught, y naught, z naught that we have given. Now we could move this over and we could have n dot r needs to equal n dot r naught. So we now have vector equations of the plane, and we put that equal to 0 and we could move that over. So let's look at these vectors that are involved in the vector equation of a plane and put them in their component form so that we can come up with a scalar equation for the plane. So n, we are going to simply call the components of n a, b, and c, and we know r ends at the point P, which is x, y, z, and r naught at x naught, y naught, z naught. Both their tails are at the origin there. So if we replace these, let's go ahead and write out what n dot r would be. So we're going to dot this vector with this vector. So that's going to be ax plus by plus cz, and that would then equal n dot r naught. So here's our n and here's our r naught. N is a dotted with x naught, so that's going to be a x naught plus b y naught plus c z naught. Okay, so this is a way to express the equation of a plane, and when we think about it, x, y, and z are variables, a, b, and c are just numbers. All of this, because we're given the initial point, is just a number, and we could call that just some constant, and we're going to do that when we express this as a scalar equation. We can do a couple of things with it. If we wanted, we could call this, we often end up calling this negative d, so that when we move it over, we have ax plus by plus cz plus d equals 0. We can also express this moving it over and factoring out the a, so this would be x minus x naught, plus moving this next term, by naught term over, we'd have b times y minus y naught, and then we would have c times z minus z naught equals 0. So these are all ways to express the equation of a plane. We got our vector equation. Here we have it in terms of the various components. If we're given a point on the plane, that's our x naught, y naught, z naught, and the a, b, and c are the coordinates of the normal vector. If we look at either of these equations for a plane that we came up with, we could call this the linear equation in x, y, and z. Now we're going to see how we could tell if two planes are parallel to each other. And two planes are going to be parallel if their normal vectors are parallel to each other. So you think of when we have a plane, the normal vector could be drawn anywhere as long as it has the same direction. And we could even have this negative, scale this. It doesn't matter here as long as we get the correct direction is the big thing on the normal vector, because we could have any scalar multiple of that, and then that and a point on the plane would define the plane. Now if we look and we have parallel planes, then the normal is orthogonal to any vector in the plane, and if that's true of another plane as well, then the normal vectors are parallel to each other, and so the planes themselves are parallel. We can find a normal vector and then we can compare it to a normal vector of another plane, and if they are scalar multiples of each other, then we know that the planes are parallel. So if we had non-parallel planes, then we know that their normal vectors are not scalar multiples of each other, and the planes would then intersect in a line. And as we look at that, we can then define an angle between two planes, and it would be this angle between these two planes here would be equivalent to the angle between their normal vectors, because both of these vectors are perpendicular to their respective planes, but the angle between them then would be the same as the angle between the planes. So that's a way we can get at angles between planes. We can find the angle between the normal of the first plane and the angle between the normal of the second plane, and then we would have the angle between those. One last thing, we want to talk about how to find the distance from a point to a plane. So if we have some point in 3 space and we want to know how far it is to the plane, here's our equation of the distance from a point to a plane, but let's see where it comes from. So as we look at this plane and we pick this point P1 somewhere that's not on the plane, and we want to know the distance. Remember, distance is always perpendicular, so we want to find D. And if we have then a point on the plane and we have a vector defined then that runs from the point on the plane to the point we're trying to determine the distance between, call that vector B. Well, this D is just the scalar projection of vector B onto this normal vector to the plane here. So when we have that vector that runs between those 2 points, if we can figure out the projection of B onto the normal vector, we will have the distance. So that's what we want to do. We're going to find D, and it's going to be the component of this B onto normal vector N. And we actually want the magnitude of that because we want a distance. Okay, so remember that is when we want the scalar projection, it is N dot B divided by the magnitude of N, but we want to take the absolute value of that because we're interested in the magnitude. Okay, so let's look at this, and we are going to have our vector N have components A, B, and C then. And our vector B, well, B runs from P0 to P1, so we can see what that's going to be. That's going to be x1 minus x0, y1 minus y0, and I didn't leave enough room here, z1 minus z0. So we now have our B. Now looking at what we need here, we also need the magnitude of N, so we can find that magnitude of N. That's going to be the square root of the sum of each of the squares of the components. So there's our magnitude of N. So we could go ahead and dot N dot B. That's going to be A times x1 minus x0 plus, then it's going to be B times y1 minus y0, and then we've got C times z1 minus z0, And then we need to divide that by the magnitude of n, which is the square root of a squared plus b squared plus c squared. And then we saw that if we distribute this a to this minus x naught and the b to the minus y naught and the c to the minus c naught, that is just a constant, and we can combine those and we called that d. And so we have our distance. We want the magnitude of this, or the absolute value. This is just going to be a number, so we're going to put absolute value signs on it. And here we have our ax1 plus by1 plus cz1 plus d. And then we've got our absolute value dividing it by the magnitude. So given any point not on a plane, you can find the distance to the point on the plane with this formula.